A minute, so I should be able to do it here also. I am not able to do here. Here it is. Record to cloud. Okay. Fine. Okay, so let us start. Okay, so let me just open my notes. Just a minute. Where my desktop runs away where the Zoom is there. Okay. Yeah. Okay, so quick recap. What we saw was till now is that we saw that what are scalars? Vectors, tensors, and scalars and vectors are just special cases of tensors. Okay. And then we saw that covariant, contravariant, and mixed tensors. Okay. Then we saw the concept of contraction of nth rank tensor to a n-2 rank tensor. You understand this, right? You go and look at it. You understand this, right?
Yes, yes.
Okay. And then we had the concept of symmetric and antisymmetric tensors. And then we said that strong principle of equivalence can be expressed in mathematical form if equations of physics involve, equations of physics can be expressed as tensor equations. And that is because if it is expressed a tensor equation, you have one tensor equal to another tensor. When you transform from one coordinate to another, all tensors transform in the same way. And so this common factor cancels out. And the tensor in the new frame, and the equation is valid for the tensors in the new frame also. Is this all right?
Yeah. Yes.
Okay. Fine. Okay. Now we will go to an important tensor which is very central to general relativity, which is called the metric tensor. Okay. It's called the metric tensor. Who is that? Is it? Okay. Now, what is metric tensor? See, we already came across a quantity called line element. And this is an invariant quantity. It's an invariant quantity. When I say invariant quantity, uh, this quantity is a scalar under any coordinate transformation. Now, to give you an example, let us consider a Cartesian 3D. Okay. Yeah. So I have dl square is equal to dx square plus dy square plus dz square, which let me write it in terms of a generalized coordinates x1, x2, x3. So I have dx1 square plus dx2 square plus dx3 square. x1, x2, x3 are just x, y, and z. And so I can actually write it in a more general form as g mu nu dx mu dx nu with g mu nu given by 1, 0, 0, 0, 1, 0, 0, 0, 1. This is basically Pythagoras theorem. Now, what it says is, in 3D Cartesian system, this quantity, I will just call it quantity right now, this quantity, given the coordinates, this quantity defines what is the concept of distance. Okay. So now suppose I have spherical polar coordinates, 3D. Then I have dl square is equal to dx is equal to dr square plus r square d theta square plus r square sine square theta d phi square. Hi, Anirudh. Anirudh has joined, right?
Yes. Yes.
Yeah. Okay. And again, in terms of a generalized coordinate, I will write this as dx1 square. This x1 is not same as the previous x1. This just says the three coordinates. It can be written in terms of three coordinates. dx1 square plus, now you have x1 square dx2 square plus x1 square sine square x2 dx3 square. which of course I can write it as dx1, dx2, dx3, 1, 0, 0, 0, x1 square, 0, 0, 0, x1 square, sine square of x2 multiplied by dx1, dx2, dx3. And so, if I write dl square as g mu nu, dx mu, dx nu, then this gives g mu nu in this case is 1, 0, 0, 0, x1 square, 0, 0, 0, x1 square, sine square of x2. So it is the same 3D space, just that I have changed the coordinates from Cartesian to spherical polar. Okay? Yes. Now, just as an example, suppose I take the case of a two-dimensional. So let me just take it to the next page because I don't want to skip the page in between. Okay. Right. So I have this. Now let me consider a two-dimensional case. I have 2D Cartesian, which is trivial. Here, what will G mu nu be? It will be 1, 0, 0, 1. If it is 2D polar, it will be dl square is equal to dr square plus r square d theta square is equal to dx1 square plus x1 square dx2 square. And so I have g mu nu is equal to 1, 0, 0, x1 square. Now let me consider another case, which is again a two-dimensional surface, but these are all flat. Okay, it's just polar coordinates is just a way of expressing these coordinates, that's all. But now I go to a space which is explicitly non-flat, which is the surface of a sphere. So I will consider 2D 2D surface of a unit sphere, which I will call r equal to 1. Then on the surface of this, I have dl square is equal to d theta square plus sine square theta d phi square. Now my x1, x2 are theta and phi. And so I will call this x1 square plus sine square x1 dx2 square. And now I will have g mu nu is equal to 1, 0, 0, sine square x1. Okay, so you see the difference between these two. Okay. Now, as an example, suppose I have these are all spatial. Suppose I have a 4-dimensional Minkowski space. Okay, so let me just compactify it a bit. Maybe I will give a different color to the two-dimensional thing. Okay. Okay, and now I go to 4-dimensional Minkowski space. In a four-dimensional Minkowski space, I have the line element dl square is equal to dt square minus dx square minus dy square minus dz square, which is equal to dx naught square plus, no, minus dx1 square minus dx2 square minus dx3 square. And so my Gij, now you just notice, I just following the convention which I told you, that when it is a four-dimensional coordinates, including time, I will use, Latin alphabets. And when it is just three-dimension, I will use Greek alphabets. That's what I am following. So Gij is equal to 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Okay? And now just an example, which we will come to later of this kind of a thing, but just an example from cosmology that when we have a homogeneous isotropic universe, which is closed, k equal to plus 1. I briefly told you during the workshop what is this. This is just that, when in the Newtonian language, when the velocity is less than escape velocity and it collapses back. Okay, but we will take the geometric interpretation later. For this, I have ds square is equal to dt square minus a square t d chi square plus sine square chi d theta square plus sine square chi sine square theta d phi square. And so if I identify chi, t as, not dt, t as x0, chi as x1, theta as x2, and phi as x3, then my Gij for this turns out to be 1, 0, 0, 0, 0 minus a square as a function of t, 0, 0, 0, 0 minus a square t sine square chi. Write the 0 slightly away. And then 0. And then 0, 0, 0 minus a square sine square chi sine square theta. If this is the thing, then I will get ds square. So you see, and you understand, what's going on? The last one, of course, I'm just giving you as a prescription without telling you how we get it. But if the ds square is given like this, Gij is given like this. That you understand, I suppose. Is it all right?
Yes, sir.
Yes.
Okay. Okay. So these are some various examples. Now let me come to more about metric. First of all, what I would like to point out is above examples Gij or G mu nu are all diagonal. In general, it need not be so. Okay? I can always do some strange, suppose I take even the Cartesian system and do some strange, like X, Y, Z, and I take some strange functions and define three new functions, I may not have G mu nu as diagonal, right? But that is, as long as they are linearly independent, it's a legitimate coordinate system, may be very inconvenient. Are you with me?
Yes.
Okay.
Yes.
Now, some points. Uh, One, metric tensor has in it encoded the nature of space or space-time. Okay. What it means is we have been talking about flat space and curved space-time and so on. This information is in the metric tensor. However, there is a catch. It is not easy to extract that information. And that's why we do all these things. So one of the things which you keep in mind is if space, I'll call it space-time, but it is valid space or space-time or whatever. Okay. If space-time is flat, Gij can be expressed as 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1, which is the Minkowski metric. So it is possible to express it like this. Now, if space-time is flat and Gij are constants, okay, maybe not even diagonal. Then you know from matrix mechanics that you should be able to symmetrize a matrix. Okay, and so it means that by coordinate transformation, by specific coordinate transformation, Gij can be brought to 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. So is this point clear?
Yes.
Ah.
You are saying that if Gij are constant, space-time is flat.
Yes.
But in the case of polar coordinate, if you take this thing, then it's 1 r square, isn't
R
it?
is not constant. R is a variable.
So you are saying Gij is
When
r
I say
constant.
constant, I mean independent of coordinates. Because R is a variable, right? In polar coordinates.
Yeah.
Okay. So this is, so look at it this way. Now, if Gij is constant, I can always do a symmetry. I can always do a transformation, a similarity transformation, and bring a matrix to diagonal form. And once it is diagonal, I make another coordinate transformation to scale all the coordinates to make the Gij 1, -1, -1, -1. Okay, is that fine?
Yeah.
I mean, so let me just explicitly. So suppose I have ds square is equal to, it is g mu gij dxi dxj, which let me now put it as dx vector transpose into the G matrix times G vector, dx vector. Is that all right?
Yes.
Okay. Now I will do this dx transpose S transpose S or S inverse. So S transpose S, G, S transpose S, dx. Okay? And so now I choose my S so as to diagonalize G. And so I call S dx as some d xi vector. And so dx transpose S transpose equal to d xi transpose. And I will call S G S transpose as a new vector G prime, a new metric G. And so my ds square is equal to d xi transpose G matrix d xi. And this matrix is diagonal. Okay? Which means that G prime is equal to something like A0, 0, 0, 0, B, 0, 0, 0, 0, C, 0, 0, 0, 0, D. It is diagonal, but the diagonal components are not equal. And now what I do is, I define my new quantity d eta 0 as square root of a times d xi 0. D eta 1 is equal to minus square root of b d xi 0. Is this correct? Just a minute.
Won't there be an I here? Iota.
Minus b. D eta 2 is equal to square root of minus c d xi, sorry, 1, 2. And d eta 3 is equal to square root of minus d d xi 3. So, so in terms of this, so now, so what I can now write this as, this can be written in terms of eta. I have ds square is equal to d eta transpose 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1 d eta. Are you with me?
Yes. Yes.
So I have brought it to a form which is the Minkowski metric. Now remember that where is the constant thing goes? It is because G is a constant that if I choose S to be a symmetrizing matrix at one point, the same symmetrizing matrix applies throughout space. That is where the constant nature of G comes. Okay? Do you get this?
No, can you repeat the last statement
So if
again?
suppose G was not a constant,
Okay, so
then
like
while doing this symmetrizing, I will have to use the symmetrizing matrix S has to be different at different places. Okay?
hmm.
Okay.
So it will be
So that is
different
how
at
the
different
constant
places.
nature of G comes. So if there is a constant, then I can always write it as a Minkowski metric. And that is what I am saying here. Okay. But there is a catch here, which is if Gij is not constant, that is Gij depends on coordinates, it does not mean that space-time is non-flat. So it means that if Gij is constant, you are sure it is flat. If it is not constant, it may be flat, may not be flat. As an example, spherical polar coordinates describe flat space, flat 3D space. But G mu nu is equal to 1, 0, 0, 0 r square 0, 0, 0 r square sine square theta, which is not a constant. So it means that just by looking at Gij, I cannot always say whether the space is curved or flat. Okay? Is it clear?
Yeah.
Yes, yes.
Okay. But there is an interesting thing here. And that is, I said if Gij is not constant, space-time may be flat, may not be flat. But if space-time is not flat, we can never have a Gij which is independent of coordinates. This is an important thing. Do you understand this? See, for example, take the case of 2D. Okay. 2D Cartesian, I had G mu nu as 1, 0, 0, 1. 2D polar, I had 1, 0, 0 r square. But by coordinate transformation, I can convert this to this, right? From polar to Cartesian, right? Do you understand?
Yes.
See, what I'm saying is, when I have a 2D flat, The 2D flat space can be described either by Cartesian or by polar. In polar, you will have a coordinate dependent Gij, G mu nu, but I can always make a coordinate transformation to Cartesian and make it like this. However, if I take 2D spherical surface, then Gij is equal to 1, 0, 0 sine square theta and no coordinate transformation can make Gij 1001. That is the important. This is the hallmark of curved spacetime. You see, you take this spherical surface, you do whatever. You can never convert the Gij. You may be able to convert the Gij as 1001 at one point, but then another point it will be different. Do you get it?
Yes, sir.
Yes, Sesh.
Yes. And it has to do with the fact, suppose I take a cylinder. Can I make Gij flat?
Yes.
No,
Why?
because it
Okay,
is
we have both
curved.
the answers. No. Okay. I will tell you what is the thing. Here it is flat. And just to see this, you can make finite number of cuts on a cylinder and lay it on a flat surface. Right? So I can take a cylinder and I can cut it longitudinally and open it and lay it on a flat surface. Spherical surface, you can never do it. Right? You take a sphere, you do whatever, you can't make it coincide with a flat surface, right?
No, that
The
violates like
Yeah.
some topological behavior,
It
right?
is not topological. It is not topological. It is not topological.
Isn't it? No,
Topological has
isn't it
nothing in which.
topology?
No, this is not to do with
Can't.
topology
Yeah.
completely. Topology
Okay.
will, I mean, this not completely topology because you see, topology allows you to what you call not modify distort it.
Yeah,
See,
but without pinching, without any singularities.
no. So suppose I have an arbitrary shape. So suppose I have a flat piece, infinite flat sheet, but in the middle somewhere there is a mountain.
Okay.
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 This is not flat. You can never make a coordinate transformation and get rid of G mu nu everywhere as uniform. Although it is topologically flat,
What I'm
I
trying
can
to say
always
is,
distort it and make it flat
what I'm trying to
without
say
punching
is,
holes.
if I'm taking a
Ah.
cylinder, if I want to make it
Ah.
flat, I can, because you can basically unravel it, you can distort it, and it's possible to make it flat.
Yeah. But that is not to do with topology.
Okay.
Topology is a very different thing.
Okay.
What
Okay.
I'm saying is, suppose I have a cylinder which is not a uniform cylinder.
Okay.
Okay. Topologically, it is same as cylinder, but you can't
Yeah.
unravel it and put it on a sheet of paper.
Okay. So you mean like to say there is some surface,
Yes. So for example,
like
in a cylinder,
variations or something.
suppose I have a cylinder like this, then I can put it as flat. But I have, suppose, a cylinder like this. Then unless I distort it, I can't unravel it and put it. So in other words, I can roll the cylinder on a flat surface and every part of the cylinder will touch the flat surface somewhere or the other. Whereas if I roll a sphere, that won't happen. If I roll this shape, it won't happen. There will be some regions which will not touch the flat surface. So it cannot be made to coincide with a flat surface.
Okay.
And this is the property which is, I mean, this all goes into differential geometry. I will not go into it. But this is the property which is actually coming out in the form that the Gij can never be made constant on that thing. And this is the hallmark of curved spacetime. So in other words, when you say in general relativity, curved spacetime, you mean it is described by a metric which do whatever coordinate transformation you want, you can never convert that metric into a Minkowski metric. That is curved spacetime. All right?
Sheesh, when you said that three-dimensional, that flat surface polar coordinate, that one, just show me that one, that formula, that 1 r square, r square.
This one. Hey, wait a minute. What is happening? Why is it not moving? Oh, sorry. This one, right? Anil?
Yeah, yeah.
Huh.
And in
It has got r square, it has got r square sine square theta.
I'm saying that what is the difference between this one and the next one, like 1 and 0, 0 sine square theta?
Oh, okay, okay. So this is the description of three-dimensional space in spherical polar coordinates.
Yeah.
Here there are three coordinates, r, theta, and phi. In the other one, it is a given sphere. It's a two-dimensional surface. So r is no more a coordinate. It's only theta and phi.
Okay.
Particles don't move along r, they reside on a two-dimensional spherical surface. Hello?
I'm actually confused. I don't know why, but because this flat 3D space, I don't know.
Pardon?
Can you explain it further?
No, basically, what it in a very rough way, you can say that in 3D space, the existence of R gives me an extra degree of freedom to adjust things to make it flat.
Okay. Okay.
Whereas in a given two-dimensional surface, I don't have that freedom. So it is stuck in a two-dimensional flat surface. And also, this is a three-dimensional flat space. Spherical surface is a two-dimensional non-flat space.
Okay. Okay.
Okay? Anil?
Yeah. Yeah.
Hey, you're behaving like an art movie here. I mean, okay. So that is the thing. So, in fact, this is rightly pointed out. You may say that it's so similar. Why is it different? That is because it is immersed in three dimension and there you have an extra degree of freedom to move things around. Whereas once you have a two dimension, you don't have that degree of freedom. You are stuck with that given radius.
Okay. Okay.
Okay. Fine. So this is now the question arises that, look, suppose I am given a GIG. I want to say, somebody asks, is it curved or is it flat? Now I can make some coordinate transformation and say that Gij, I'm not able to make it flat. But that does not mean that no transformation exists which cannot make it flat. There are infinite number of transformations possible. Even if in one transformation I get Gij as Minkowski or flat or diagonal, I mean as constant, I can call it flat. But practically, how do you do? See, if you make a transformation and you get Gij as constant, I will say, okay, it is flat. But if I make a transformation and I don't get Gij as constant, I cannot say that it is not flat because there may exist some other transformation which can make it constant. Do you understand the point?
Yes.
Yes.
Okay. So conceptually, this is what it is. Although in practice, this is not the way you can test for non-flat space. Okay. And that's where the whole tensor calculus comes. Is it fine?
Yes, yes, fine.
Okay. Right. Okay. So now let us go. Okay. Now let us go further. And so, okay. So here there is just one more thing which I want to mention. I have. See, I had mentioned that if I had a tensor is equal to some object multiplied by tensor, then this is also a tensor. I also given a problem on this one, but I also mentioned this, remember?
Yes,
Yes.
yes.
Okay. Fine. Now, so now let me write ds square equal to Gij dxi dxj. This quantity is a scalar, which means tensor of rank 0. This is a contravariant vector because the whole contravariant vector definition was the way dx upper I transforms. Okay? Contravariant vector, which is tensor of rank 1, which is true for this as well as this. And hence, dxi dxj is a tensor contravariant of rank 2. Since this is a scalar, first of all, implies Gij equal to tensor. And since ds square is a scalar, Gij has to be a covariant tensor of rank 2. So that this contracts with I and j and makes it a scalar. I told you, right? When you contract a tensor, so look at it this way. Yeah, so when you make two indices equal, then the whole rank gets down by 2.
Yeah.
Right? So this is why Gij is a tensor. And so it has all the properties of a transformation of tensor. So it means that Gij bar is equal to dx a by dx bar I dxb by dx bar j gab. Tensor transformation. Shall I go ahead?
Yes, yes.
Okay. So this is, see, I'm sorry I keep asking because, in a class, I can look at people's faces and see whether I can go ahead or not. Here I can't. Okay. So Gij is a tensor. Okay. Now let's go ahead further. Is it time? Okay. Yes. Now we next come to a very important thing, which is tensor calculus. Till now, what we were doing was tensor algebra. Now we'll go for tensor calculus. Okay. And so why is it important? Because differential equations play an important role in the mathematical formulation of a physical law. Hence, differentiation of tensors has to be dealt with carefully. Okay, and there is a law, and this is where the devil of GTR comes out when you do tensor calculus. So let us consider a very simple thing to begin with. I have considered a scalar phi as a function of x in one coordinate system and phi as a function of x prime in another coordinate system. Okay. Now, we know we already defined that suppose I have del by del xi phi x. Okay. This was the whole definition of covariant vector, right? As a partial derivative of a scalar. And so this is equal to del x bar j del xi del phi by del x bar j. Okay. So if I call del by del xi phi as a covariant vector I, and okay, here I want to say something, and this is equal to del x bar j by del xi. Since these two are equal, f prime. Since phi of x is same as phi prime of x prime, I will write it as phi. So not, sorry, what am I writing? Phi bar of x bar is phi bar x bar by del x bar j. So I write del phi bar by del x bar j as a bar j. And so both these together mean that ai is equal to del x bar j by del xi A bar j. It means two things. One is AI is covariant and there is no surprise. Just like I said, dxi is contravariant, this is the way I defined covariant vector. That is, those vectors which transform as a partial derivative. So that is not the problem, but that's the point. What is interesting is, what it means is, this implies that partial derivative of a scalar
Yeah, it's clear.
Okay, fine. So partial derivative of a scalar transform as a tensor. Very good. Now comes, as I was saying, the devil will raise its head when I try to differentiate a vector or a tensor. And I will tell you why that happens. It happens because, okay, so let me just mathematically first do one thing and then I will tell you the physical interpretation of that. Okay. Then, so I will say partial derivative of a, say to begin with, I will take a contravariant vector. So I will take AI and I have del by del xj AI. I make a transformation x to x bar, making A to AI bar. Okay. Now, this quantity will be equal to what? First of all, it will be del by del xj. Now I will transform AI as in the A bar form. So it will be del xi by del x bar j, A bar j. Are you with me? Just partial derivative. I mean, this is just definition of covariant derivative. Okay. Sorry, not covariant, contravariant derivative. Okay. It's all right. It's okay now. I mean, please stop me whenever it's, because it's a very intricate thing. Can I proceed? I mean,
Yes, yes.
Yeah.
Yeah, you go ahead. Yeah.
okay. And what is this equal to? Now, this equal to del by del x. Sorry, del x, I will call it A, del x bar A by del x j, del by del x bar A, del xi by del xj, A bar j. I have just written this partial derivative thing here. I mean, law of partial derivatives. But now this is equal to del x bar A by del xj, del by del x bar A, del xi by del x bar j into A bar j plus del xi by del x bar j, del by del xj, del x bar A, del by del x bar A bar j. Are you with me?
Yes.
Okay. And now we can write this as del x bar A by del x j, del 2xi by del x bar A del x bar j, A bar j, plus del xi by del x bar j, del x bar A by del x j, del A bar j by del x bar A. Now, suppose I call del xi by del x, say, j, as some quantity. I am not calling it a tensor. Some quantity Sij. Okay? It has one index up, one index down, and I call it Xij. Then I see that this quantity is Sij is equal to del x bar A by del xj, del 2xi by del x bar A del x bar j into A bar j, plus del xi by del x bar j, del x bar A by del x j into S bar j A. Are you with me?
Yes, sir.
Yes,
Okay.
yes.
If you see this portion, if this portion was absent, this portion, then it would have, the transformation is that of a tensor. But the fact that this portion is there plays the spoil sport. It means that partial derivative of a vector in general is not a tensor. Okay. So, we have learned that partial derivative of a vector is in general not a tensor. When will it become a tensor?
When
And
we
this is a very
subtract,
interesting thing here. When will it become a tensor?
When that term vanishes, like if the
Yeah.
when we subtract that extra term.
Yes. So, yeah. No. So if the extra term were 0, then this partial derivative would have been a tensor, right?
yes, yes.
Okay. When will the extra term be 0? The extra term will be 0 when the second derivative del 2xi by del x bar A del x bar j is 0. And when will that be 0? When my transformation
Linear
between
tensor.
x and x bar is not a linear transformation, but a non-linear transformation. If it was a linear transformation, the first derivative will make it constant and the second derivative will kill it. Do you get the point? It's a very important point.
Yeah.
Okay.
So in
And now you can actually suddenly realize something. You know, when you do Lorentz transformation, it is a linear transformation. And this term would never appear there. And that is why when you are doing special theory of relativity, this complication of partial derivative causing a problem never came up because you are only talking about linear transformation. And the first term was automatically 0 whenever you do that.
Hmm.
But when you do general relativity, you are doing a general coordinate transformation, including nonlinear transformation. And that is when you can't neglect it. Is this clear?
Yeah.
Yes, yes.
Okay. Now, so it means that there is something funny happening in general relativity. What is it? So I will just stop it here, but except to say that what is basically happening is when you do a linear transformation, the unit vectors in both the things, in both the coordinate system, are linearly related. The problem comes because the coordinates themselves are sort of moving. So when you do a partial derivative, you are subtracting the vector from one point and a nearby point. When you are doing this, you are talking about the components of the vector. Now the components of the vector not only changes because the vector itself is changing, but it also changes because my unit vectors have changing their direction. You understand?
In polar coordinate, yeah? This thing, sir.
Just polar coordinate is an example. So when you go from polar coordinate to one coordinate to another, you are at one point is from r vector to another point. But I vector and the I vector are two different things is the same. So and that's why in polar coordinates is nonlinear related. So the problem is like, okay, that's a good thing. Now, if suppose you have a voice and you have a dictionary, you can use the voice and the dictionary to find out the meaning of that voice. If my voice changes, then the dictionary will indicate that it's a different object. But if my voice changes and my dictionary also changes, then I have to subtract the artifact of the change in dictionary, in our case, the artifact of the component change because of coordinate change, and extract the physical change in the vector. Do you understand this point? It's a subtle point.
Yeah. Yes.
Hello.
Yes.
Yes.
Anil, Anirudh,
Yes,
Can
yes.
you repeat it once?
Harish,
Can you repeat it once?
So what I am saying is, the component of a vector, how do you take a component of a vector? You take the vector, take a projection on the unit vectors. Okay. Now when my coordinate is changing, my unit vector is also changing. So it means, okay, so let me give you an example. Suppose I have a free particle going in this direction. Okay. And now this is my coordinate system. Y, X. It means that Vx is equal to constant and Vy is equal to constant. And this is equal to V and this is equal to 0. And this is a free particle is moving with a uniform velocity. Is that all right?
Yes.
Is it okay?
Yes,
Yes.
yes.
Now I describe in terms of polar coordinates. Here, at this point, Vr is 0 and V theta is not equal to 0. Whereas when I take here, my r vector is here, velocity is here, so there is a Vr which is not equal to 0. So it means that the component of the Vr is actually changing, or V is actually changing. But you know that it is a free particle, the velocity should not change. Why is it changing? It is changing because the r unit vector is changing as the particle is moving. Here it is r unit vector. Here, when it was here, it is here. When it was here, the r unit here. So the unit vector itself is changing the direction. So the component of the vector will evolved due to two reasons. One is its intrinsic change, plus the language itself is changing. The projection is changing because the unit vector is changing. And if you want to talk about a physical change in a vector, we need to have a proper mathematical formalism to extract the coordinate artifact of that and extract out the physical change in the vector. And my physical laws should talk about only this physical change. Is it understandable? Can you understand this? Get it?
Yes.
Hello?
Am I audible?
Okay, Snigdha, you are very quiet.
Got it.
Okay. Yeah. So the thing is, so this is the whole thing. So now this is the whole thing which leads to what we call a covariant derivative, which basically says that this is actually the physical change in the vector. The other is all a coordinate artifact, and clearly your physical laws should talk about only the physical change in the vector and not the coordinate artifact. So the important thing which has to be done is to set up a mechanism to subtract out the coordinate artifact and extract the real change in the vector so that we can use it for our physical principles. Is it okay? I'll stop with this. Hello?
Yes, yes.
Yeah.
Yes.
Yeah,
Right. Any questions?
yeah, in that case, I'm still confused that polar coordinate, that thing, that why I'm confused is like when I think of like, can we say it like coordinate itself is something like flat or curved? We don't talk in that way, isn't it?
No. The coordinate is not curved off. The space is curved or fat.
Yeah. So sphere is curved thing,
Yes.
isn't it?
Yes.
So how can I construct a matrix so that it says that it is a curved thing like that?
No, that's what I'm saying. So if you make a metric, you can go to any coordinate transformation within the theta phi. You will never be able to get it in which it is 1, 1, 0, 0. Because it's a spherical surface, it's a curved surface. Anil? Okay. And remember, you see, when you're talking about a spherical polar, you're talking about a different animal. You're talking about three-dimensional space. When you're talking about the surface of a sphere, you're talking about two-dimensional space. So completely different. Okay.
In that 1 and r is that sine square theta, what was it representing actually? Like it was surface, isn't it?
Yeah, so theta and phi are the theta and phi, the latitude and longitude. Okay. See, that is why, you have this whole thing about when you want to project the globe, it's a very non-trivial thing. You'll never be able to project the globe on a flat surface.
Yeah. I get it.
So it is the same thing. See, if you were able to put a flat Minkowski thing, I should be able to project it onto a flat surface. Okay. Okay. I will draw.
Yes.
Okay. Bye.
Good night.
Bye. Good night.
Bye. Good night.